of ITS Iceland, and like Jenny said, we are part of ITS Nordic Plus, which is a growing network of, I would like to say, nerds that are interested in technology and mobility and infrastructure. But as you all know, nerds are the ones that rule the world, so we are just proud of that. But why are we having this webinar today? The webinar on ITS and how it can help with natural, well, not the natural catastrophes itself, but the monitoring and predicting and informing that's necessary around these natural catastrophes. Well, the idea originated here in Iceland because of we've had almost 3 years now of earthquakes, and I think it's 2 years of volcanic eruptions that have been erupting every few months, and everybody has been almost following it on the news, seeing how the emergency actors are trying to assist people in evacuating, trying to take care of the infrastructure. And it's just a very actual subject in Iceland right now. And when we discussed this idea with our Nordic Plus friends, it quickly became clear that each and every country is dealing with their own form of natural catastrophes. We have floods in Denmark, we have extreme weather conditions in Finland, we have rock slides in Norway, and so on and so on. And we're going to hear about that all today. And we're also going to discuss how each country is using the technology to assist in these matters. And hopefully we can also discuss if there's a room for some improvement. We have 4 great presenters here today. We have Marius from Norway, we have Halldór and Víðir from Iceland, and Janni from Finland. Each presenter is going to talk about around 15-20 minutes, and then we're going to take questions right after each presentation. And you can post the questions in the chat, but you can also raise your hand if you wish to talk. If you wish to talk, I would like to ask you to put your camera on. And yeah, with that said, I don't think I have anything more to add to this. So over to you, Marius, with the first presentation.
Thank you very much, Celia, and thank you so much for having me attending this webinar. See if I can show you this presentation. Yes. So, my name is Marius Kramer. I'm representing the Norwegian Natural Hazards Group. In Norwegian, it's called the Nasjonal Rassikringsgruppe, and we actually recently changed our name into English so that more people get to know what we are doing and what we are about. The title is The Increase of Rock Slides and Avalanches, and what technology and ITS can do to predict and to prevent more. First of all, the Norwegian Natural Hazards Group, we are a lobby organization. So I'm head of the administration, and we have 8 politicians from the eight most avalanche-prone regions in Norway that are working very hard in their own regions and also to lobby the national governments in order to prevent the dangers from natural hazards and to ensure safer travel on our national roads and our county roads throughout Norway. And the mandate is shortly to put the issues of avalanches and rockfall protection on the political, hopefully national agenda, and to get more people engaged in the natural hazards and the road safety measures. And we also, of course, lobby for more funding to get these protective measures in place. And we have been around for about 25 years now, and we have seen a growing interest in our work, and we feel that the political parties in the National Assembly, the Stortinget, are backing us all the way. So we're very happy to have that kind of support. So to our challenges. In Norway, we have hundreds of fjords, we have a long coastline, and we have mountains ranging with peaks above 2,000 meters above the sea level. We have very steep fjords, and the slopes are prone to natural hazards, particularly avalanches during winter. And many of our communities are located at the seaside, and they are heavily dependent on roads along the shore for transport of people, goods, and services. We experience loss of life, damage to property and equipment, and loss of business competitiveness, and we experience that we expose ourselves to an unnecessary threat to our civil society. Just to be clear, we are focusing mainly on rockfall and avalanches, and not so much on wildfires and floods and volcanoes, but we have other experts that will talk more about that later on today. So, to give you a few examples, in Jølstra, about 5 years ago, there was a big landslide that covered also a long stretch of the road. Actually, that is a sad story. There is still a car and a man trapped underneath the rubble there, and also underneath 500 meters of water. The other one, the other picture is a quick clay incident. I think it's safe to say that it was a man-made disaster, but it took away a long stretch of a regional road in Finnmark, in the northern part of Norway. Another few examples here from Myrland in Nordland and Årdal in the western part of Norway that shows damage from rockfall on county roads. So let me see if I can show you this. This is about 3 years ago from now. If you look closely on this, I'll speed up the process a bit. If you look on the top, you can see a wet snow avalanche coming down the mountain, and there is a road and of course houses underneath, but the road is hit. And if you look closer, you can see that there is a car passing. I'm not sure you will see it, but there is actually also a car just passing before it hits the road. And this incident actually helped local authorities to also extend the tunnel that we have there already, and there is radar and fences that close the road now when avalanches are detected. Yeah. So, preparedness and climate adaptation is being increasingly important. Our preparedness depends on the roads being passable, safe, and open. Our natural hazards threaten our transport lines and vital arteries for society. And we, of course, understand that the climate change will lead to more problems with avalanches and other natural hazards, and avalanche protection is climate adaptation in practice. And this, in our view, is too important not to be given a higher priority also by the national governments. And our Norwegian Directorate for Civil Protection and Emergency Preparedness have calculated that 1 krone, Norwegian krone, spent on prevention saves 7 to 14 kroner in repair costs. So it's a good socio-economic picture there. So how is living with fear and uncertainty? We have thousands of dangerous stretches of roads that threaten to take lives and in an instant. And many of our communities and people live in fear of sending children to daycare and to school along avalanche-prone roads, in fear of commuting past avalanche areas. Our businesses experience unpredictable deliveries and significant losses due to roads being closed for long periods because of avalanches or the risk of avalanches. The risk of avalanches cause the roads to be closed for long times and are really a problem in the northern parts of Norway. Of course, we are dependent upon safe and accessible roads in Norway, and we cannot afford to lose anyone. So why are protective measures so important? Because, of course, avalanches take lives, they injure people, and they create fear and insecurity. And we believe that the safe road should not be an extra service, but as a matter of fact, a very highly prioritized task. And because freight and sea transports are very vulnerable to get to the market in the time period they are designed to be, and because closing of roads due to the risk of avalanches are not a permanent solution. And very many of the communities in Norway lack detour options, and avalanche protection is the only measure to ensure accessibility. I will give you a very tragic example from last year here close to where I live in Tromsø. There was an avalanche on Reinøya in March last year, where 2 farmers lost their lives when an avalanche came down the mountain and also killed all of their sheep and destroyed, of course, the buildings and crossed also the regional road and into the sea. The financial situation has changed, and now reality bites hard also in Norway. We just had a mapping of what it would cost to require to secure 500 of our most dangerous stretches of road. And it cost almost 100 billion Norwegian kroner, which I would say is close to 8 billion euros. So the new economic reality and our financial situation makes it unrealistic to expect that our governments or our regional governments would pay for tunnels and avalanche shelters everywhere. That would require many decades of funding with today's level of financing. And for one of the regions, actually the one I'm sitting in right now, this means 100 years of waiting, and that would be a very impossible thing to contemplate also for our politicians. So what are our possible solutions? Well, technology and innovation could be a part of that. Of course, when it's needed, we have to build tunnel, but we have to also try to avoid our so-called tunnel vision in Norway. We have had the luxury of building tunnels almost everywhere, and that the gold standard is not longer an option for all parts of Norway and all stretches of road. We believe it will pay off very well if we invest in prevention and prediction through the use of technology and innovation where and when possible. And that means alternative ways to secure against avalanches. It includes monitoring, alerting, closing, blasting, clearing, assessing the avalanche risk, and reopening the road. The pros of this is that we will try to reach an accessible or acceptable risk level to get safe roads and to increase accessibility. The investments costs are fairly low compared to investment costs on tunnel and shelters, and it's a much more climate-friendly option, and it's more flexible. And in reality, it means that it's the operation, the year-round road operation that constitute the road's security, and it requires good communication and cooperation between the different actors on the road. And using technology will also provide us with the opportunity to secure more avalanche points much faster at a significant lower cost. So we have different types of solutions. I would try to cut through these fairly shortly, but we have detection and warning of avalanche on roads through use of distributed acoustic sensing, which are fibers that can detect avalanches, and if vehicles are trapped underneath the snow. This system is capable of detecting avalanches that are impacting roads, and of course will enhance our safety. This is now an innovation partnership with the Norconsult, Norsal, Alcatel Submarine Solutions, and Troms County. We have avalanche protection, cost-effective and reliable, enables automatic detection of avalanches, and as you saw in the video, it's a real-time detection, allows you to close roads with, for instance, traffic lights or barriers. We have recently a new project here in our region when it comes to RACs, the remote avalanche control systems here in Grøtfjorden outside Tromsø, that enables avalanches to be explosively triggered remotely and avoid the need to put highway avalanche control personnel in harm's way. It's a control closure, and then you clean up and open the road. And we have now the National Road Authority, a project called the Geosphere, with the use of drones. It can help design protection measures and increase predictability. And they can be programmed to carry out repeated registration of hazardous areas, and with the help of artificial intelligence, data from such automated inspection rounds can provide early warnings of avalanche risk and indicate where resources should be allocated. And there are also places in the world where drones are used to carry explosives and work almost like cheap racks. So what's next? Here's a futuristic concept showing how artificial intelligence can aid in the prediction and prevention of natural hazards. And you see on the picture, the scene features an advanced AI control center with technicians and scientists utilizing cutting-edge technology to monitor and analyze various natural hazard scenarios. So that could be a step forward. We don't really know what kind of, let's say, tool in the toolbox that would be, but as we already know, it will be a decision-making tool. And it's going to be very interesting to know and understand more of this, and to monitor the development of artificial intelligence on this scene in the future. And of course, we will continue our lobbying for the Norwegian government to save money. We know that they can save at least 1/5 of the 100 millions if they go for more technical solutions than tunnels and shelters. And I will also try to give you a link to our ISSW big workshop being carried out here in Tromsø in September. So if you want to listen or look at that, you can click on this link when this presentation is out. And lastly, I would just mention that the Hazards Group is now moving to Canada to learn more from our Canadian friends and partners, and their experiences when it comes to technology, communication, and climate change. So with that, I will end my presentation and say thank you very much, and you have my contact information and the login to our webpage. Thank you very much.
Thank you, Marius, for a very interesting presentation. We have open for questions now. You can ask your questions in the chat or raise your hands like Jenny just did. Jenny, you have the first question.
Yeah, I was quick there. Thank you, Marius. Very interesting. Question about the technology. How do you know which technology, how did the counties reach out, or how did the counties find out about the technology? What kind of a means, how did they do it? Did they have a lot of talks to different kind of, Jesus, now I forgot all the words. Did they talk to a lot of companies, industries? And how did they reach out to that point where they are now?
Well, it all boils down to competent people in the regions and with the road authority. So for the regional roads, we have very clever people from our geo departments that are already been looking at different kind of technologies that could be optional for the different avalanche points. So it depends on what kind of measure would be the best at that specific point. But they share information through different networks, and they are very eager to learn from each other. So I feel that they have some sort of good understanding together about the different technologies, and they share information if possible through their different networks. They all recently developed these the mapping of the different avalanche points together with the National Road Administration. And for the future, of course, we'll hope that they can cooperate even harder, because this is something that requires very good cooperation, also with the industry. And I think the industry is also online when it comes to informing and being out there, reaching out for the road owners.
We have a question in the chat. What criteria do you use to choose an area? Is it the chance of avalanches, population, road traffic, for instance? Do you have some rules for that?
Yes, there is there is an old a system for assessing the risk at each point. So it's like a scale from low to medium to high, and and as the question here said, that it depends on the volume of transport on the road and how many avalanches are detected over a period of time, and so on. So there are principles to follow on how to range the different points of avalanche.
Maybe I have one question. I was interested. You have all these monitoring devices that you showed, but who takes care of informing? Is that you, or is there another? Is there like a public institution that takes care of closing the roads or informing people?
The road owners with their entrepreneurs are the ones who are doing this work, and also they are in close collaboration also with the National Road Authority, that also has this 24/7 information.
Okay.
On to all the road users.
There's one more here. How many places are monitored now in Norway?
I'm sorry, I don't have the exact number of that, but there are. I'll come back to that. Maybe I can answer that later on.
Yes, I think we're going to.
Sorry.
One more.
Yeah, one more. I promise I'll be quick. Now I even managed to find the words in English as well. You mentioned you're going to Canada before the summer. Is there something from that trip that you can share with the Nordic Plus organizations, like later on in the autumn, in order to have this knowledge sharing going on further? Because now we created this webinar, and I think there's several probably that are interested in findings from Canada as well. Is this possible, Marius?
Of course, and we are very eager to know more. They have a long tradition and long experience in dealing with all kinds of natural hazards in Canada. So yeah, we can come back to that, and if we have some good facts and experiences from Canada, we can come back and talk about that later on.
Okay, thank you.
Okay, and of course, if some question pops into your mind later on, you can always put it in the chat. But we are now going to move over to Iceland, to Halldór, Associate Professor in Geophysics from the Institute of Earth Science at the University of Iceland. He's going to tell us about Siglufjörður Road here in North Iceland.
Hello, yes, thank you very much for inviting me to be a part of this. It's well appreciated. So my field of expertise is in crustal deformation here at the University of Iceland, and I study a few other things than landslides, so that includes volcanoes and earthquakes and geothermal systems, land uplift due to glacial retreat, but also landslides. So today I wanted to tell you about a pilot project that we have in collaboration with the Iceland Road and Coastal Administration about GPS monitoring of landslide motion in northern Iceland. So why study landslides? They are a major hazard for safety and to some degree road safety worldwide. So here's a figure from Sweden, just north of Göteborg, from the Stenungsund landslide, which occurred in September 2023. And it's just a very sort of visual example of how these of what these landslides can look like. They have very different scales, both in space and time. They can be small or large and occur slowly or quite rapidly. So the motivation sort of is, when we look at figures like this, is that can we make some sort of warnings for landslide failures, and can we do something smart, and how can we augment our monitoring systems in some ways? So we have, of course, quite a bit of landslide areas in Iceland, and here's just an example from the north of Iceland, a mud flow that goes across a road. It doesn't split the road into different parts, it just goes on top of it. So there are different types of landslides, and that's something to consider. And here's sort of a textbook example of that. There can be rockfall or topple of different blocks of material. There can be these rotational landslides, which are where mass is going out away from some area with some faulting and other things. So this is actually the type of the landslide that I will be talking mostly about. We can have some planar motion and wedge motion of parts of the landslides, or complex and compound motion. And then we can have things like these flows or mud flows, and it varies really quite a bit how thick these landslides are. They can be just tens of centimeters to meters thick, and they can be tens of meters in thickness. So, and an important thing is that they also occur at different speeds. So we can have this sort of catastrophic failure, but we can also have creeping motion. And the landslide, they can transition between these modes, and often this transition is triggered by intense precipitation. And sometimes the failure is seen to be preceded by acceleration of creep. So they start forming some faults, and then they move faster and faster until you get catastrophic failure. So we want to understand better sort of motion of landslides here in Iceland, and also see what we can do to augment these monitoring systems. So there are quite a few techniques that are available to monitor how slopes are deforming. So I'll be mostly talking about GNSS or GPS measurements, but there are also radar measurements, both land-based and space-based. To monitor these, there are all sorts of different laser ranging systems. Basically, the idea is you shoot a laser at the landslide and you measure the travel time, how far it takes it to come back to your instruments. And then there are all sorts of optical techniques and using in situ tilt meters or extensometers and fiber optics to monitor how the landslides are moving. But I'll be mostly talking about the GPS here. So there are quite a bit of landslides in Iceland. This is a figure from a landslide catalog from 1900 to 2000, and it's recording just the number of recorded landslides or rockfalls. And they are concentrated in, of course, where people are living. So they are concentrated in the north and the west and sort of scattered around the south and the west parts, and then in the east of Iceland, where we have fjords with steep topography. So numerous landslides, and it's maybe also a matter just how we count. So it turns out that practically every slope in Iceland is moving. So what I'm showing here on the left is a recent study that uses INSAR data, so space-based radar data, averages motion over 6 years, and subtracts various deformation sources like plate motion and volcanic and tectonic motion. And this residual image here is showing east-west motion in this area, and the blue means that there is westward motion, and red means there is eastward motion. And this may look a little bit confusing, but if we correlate this where we have valleys and hills, we see that we have basically all of the slopes are moving, and of course moving downhill. So this is just gravity at work. But when we put this into context with the number of landslides, we see we have an infinite number of landslides. We of course have some areas that are moving much faster, but this slow movement is inherent with basically all the slopes that we have. So if we just take any sort of average slope that we have plenty of mountains that look something like this here, Mount Akrafjall in West Iceland. These hills here have slow creeping motion, maybe a few millimeters per year. So that is maybe not hazardous for roads. And if it just keeps on creeping, then that's not a major hazard. But there are also other areas which are creeping a few orders of magnitude faster. And that brings us to this Almenninga region that is in North Iceland, which is a fast and transient creeping landslide. So we are in the very north of Iceland here in a region called Tröllaskagi, the peninsula of the trolls, if you want. And there's a town here called Siglufjörður, about 1,000 to 1,200 inhabitants, and there's a road that goes here along the coastline, and it crosses this landslide area here, which is about 6 kilometers long. The road was opened in 1968, and there has been observed up to 2 meters over 1 year, and there is a fear of failure. And if we look at sort of a geomorphical map of this 6 kilometer long region, we can divide the landslide area into 3 different regions, but within them there are also plenty of sub-regions which are moving faster or showing different faulting, which are shown by these sort of green and red lines here. And of particular concern is this segment of the road here, and you see sort of these concave faults, and these are really faults that are digging further up into the landslide, and this map is from 2004, and currently some of these are exposed on the other side of the road. So, and in this location there are about 60 to 80 meters down into the sea. So this is of course a concern if we get even if it's just a small part of the landslide that goes out in these regions. So what do we see if we go in the field? We see plenty of clear signs of landslide motion. We see this fault-like motion, the down throw of some tens of centimeters, meters, and even tens of meters, more than that. So if we look at uphill, this is sort of the uppermost part of a subsegment called Tjarnardalir, and Tjörn just means like a pond, and there are these pond here, which this landslide is named after. And then this mountain, sort of where the red lines have been drawn here, they outline sort of the headscarp of the landslide, and it is now just slowly creeping down. If we take a look from the sort of frontal part, this is the fastest moving region. We see in the landscape lots of different types of faulting, transverse faulting, but also these shear zones. And these shear zones, they are always difficult for maintaining the road, because we have some mass here that is moving about a meter per year, and it is connected here to a mass that is moving slower, and the road gets pulled apart in these sections. If we go to down to the sea level, to the front of this, in some locations we can see why the landslide is moving. We have some underlying bedrock here, which is not deforming. Above that, there's a layer of weak clays, and they also act as water barriers. So above these clays, we often see water coming out. So water comes down into the landslide, and then it has difficulties flowing through the clays and is transported to the front of the landslide. And then on top of it, there is this 60-meter thick, roughly, landslide mass. So it's creeping mostly because of these clay layers which are in the area. So, for example, 2004 to 2023 in this area, there are about 18 meters of movement, relative movement that we have here. This road section gets transported here down towards the sea. So there was a master student here that was looking at motion of these landslides, just looking at optical figures, and from 1954. And here's one of these figures. It's color-coded by the speed of motion, displacement meters per year from 1994 to 2000. And the lines here show the strike of the motion, so the direction of motion. And there are a few different segments. That's sort of a hallmark of this landslide. It's very segmented. And also what comes out is that the motion varies quite a lot from one decade to the other. So it's very variable in both in space and time. There were some GPS measurements that were started in the 90s along the road, and these arrows here are showing the horizontal displacement rates. Scale bar here is 50 centimeters per year. So it's mostly this northern part that is moving, but we also have some movement at some parts here in the south. And this plot here just shows for one of these benchmarks the interannual velocity, so how much it moved in each year from 1996. And it's usually like, half to 1.5 meter per year, but it varies quite a lot from year to year. So this was sort of the information we had at the time, and we were very interested to install continuous GPS stations, which is there's always recording data, and both to use them for warning and also for long-term studies of how this landslide is moving. So we installed 9 stations in the area, locations shown here. We had one act as the reference station. Good to have one reference station as close by as possible to minimize errors. And we went with sort of, I would call this medium budget installations. We could have had an order of magnitude more expensive instruments and an order of magnitude more cheap instruments, but we decided to go with something that gave us basically geodetic grade, so very high grade data for a reasonable price. The power for the stations is solar and wind for some of the stations. Data is streamed in real time and processed using software called RDK-lib, and we are getting solutions every 5 minutes or so. And then we also do post-processing of 24-hour files, and we have sort of these few layers of data processing. So what comes out of these measurements? Here we're looking at about 1.5 years of data from the station that is moving the fastest, and we see the sort of character of motion. We have time here on the x-axis, and then we have motion in the up, north, and east components. And there are these distinct displacement episodes, and then there is not too much happening in between. So for this particular station, we have mass motion of 1.2 meters north, 0.3, and then it goes down by 0.16. And many of these stations are moving more or less horizontally, and this has to do just with the angle of the sliding plane that's beneath. If we plot here the radial motion, so just along the direction of highest motion, what is the motion of the stations over this time? We can identify 7 different periods of accelerated motion. Most of the landslide segments take part in these, at least I would say, most intense events, but it varies quite a bit for the smaller events, which ones are moving and which ones are not moving. We also see that some landslide segments are moving, continue creeping throughout the winter, while some other ones, they just kind of stop moving over the winter. So it's very variable. The maximum rates we have seen is about 3.5 centimeters per day in November 2022. And we also find that most of these transient deformation events are related to rainfall events. And if we look at that, there was a meteorological station installed in the area as well with a rain gauge. And we have here east deformation of our fastest moving side and cumulative precipitation here in blue. And over 1 week here or over a few days, there was quite intense rain, or we find it is intense, 120 millimeters over 5 days. And when we come to some level, then the landslide starts moving, and the fastest motion of the landslide actually occurs after the rain has stopped. So it keeps on moving quite a bit after the rain stops. So here's another example of one of these rainfall events. Here we're looking at these 5-minute solutions, what they look like, and same sort of coloring here, just showing basically, in this case, we already had the landslide motion ongoing after a previous rainfall event, and it was kind of decelerating. And then there was a intense rainfall that occurred, 70 millimeters over 3 days, and the landslide speeds up. And I think it's interesting that it speeds up very sort of abruptly, so like a change in mode of the landslide. So just to give you insight into what we're sort of learning from this data. So it's quite obvious that the precipitation is really key if we want to give warning. So the GPS doesn't warn us ahead of time if landslide motion is imminent, but we really need to look into the main triggering factor, which is the precipitation. And it's difficult to forecast precipitation in mountainous areas because you tend to get more or less precipitation on the lee side of mountains and complicated sort of mountain effects. So there are contracted services, company called the Veðurvakting, the weather monitoring company, and they are working with the road administration to make better or improved precipitation models. And it's tricky because usually these weather models are made in certain grid points, and it depends quite a bit where are these grid points and how to interpolate between them and things like that. So this is very much a work in progress. This behavior of landslides to show this transient motion connected with high precipitation events, this is seen all around the world, and there are lots of landslides that are a very sophisticated monitoring instrumentation. Here's an example from the Spriana rock slide in Italy, and basically showing the importance of looking at what the groundwater levels or groundwater pressures are doing inside these landslides, since they are the main triggering effect. Here's an example of a peak velocity 14 centimeters per hour. So maybe one way to think about these landslides in terms of just the physics, we think about them like a leaky bucket. So it's called porous media. We pour in some water. If we pour it in very slowly, then it just leaks out sort of the bottom without raising much the water pressure in the landslide. But if we pour very fast over some considerable amount of time, the water level goes up and we get more water pressure and also weight inside the landslide, and it is more prone to failure. So these kind of porous media models are needed to basically define what detection thresholds we need for the different landslide masses. So this data is being worked into the monitoring system of the road administration, but there are challenges. So there are these closing gates that have been installed on either side of these landslide segments. But there are, like I said, challenges. The GNSS time series are noisy. Here I'm showing a 12-hour segment movements in north and vertical component, and the scale here is plus minus 100 millimeters. So sometimes we get these excursions in the data due to, for example, disturbances in the ionosphere, which affects the GPS signals. And it's at the time when you are looking at the data in real time, you don't really know if this is real deformation of 15 centimeters or not. So it challenges and really puts some poor limits, I would say, on the kind of detections that we can do with only the system. But we are working on improving the processing and augmenting it with different things to help improve. Also challenge with precipitation forecasts and the landslide response is also somewhat randomized. So you don't always need exactly the same type of rain to trigger motion in it. So to kind of summarize, we have many creeping landslides in Iceland, and we have creep rates up to 1 meter per year in this area. Some regions can have higher rates. The motion is transient, it's seasonal, it's triggered by high precipitation. The relation to rainfall is not straightforward, and some sort of porous media modeling is needed really to use it successfully for warnings. And we are working this into the warning systems of the Iceland Road Administration. So with that, I think I just conclude. Thank you.
Thank you, Halldór, for a very interesting presentation. And I have a few questions, but I'd like to ask the room, if I say so, if they have some questions before I start with mine. Well, I was just interested. You said that there are some places in Iceland that have higher rates than 1 meter.
Yes.
Are those places? Are there no roads then there, or why is this place so interesting?
Yeah, this place is interesting because it really affects the roads in the area. We have another landslide which is on the west side of the Katla volcano in South Iceland, and that landslide is moving. Well, it's moving at about a meter per year now, but it's basically a mountainside that is slowly collapsing, and it was moving at more than 10 meters per year during the mid 2000s.
Okay. And what the monitoring system? You said you're connected to the road administration. How does that work?
Yeah, so we are in the process of implementing that. So we basically get out text files with displacements, and they get transferred into the monitoring system. So the road administration in Iceland, they are monitoring, of course, all sorts of meteorological data, optical data, web cameras, and other things. And the idea is that this data goes in as part of their monitoring system.
Okay. Anybody with? Forgot to turn on my chat. That's maybe better. Yeah, we already have 2 questions here. You said that you're cooperating with the emergency services. Is there a response plan ready? And it's pretty much the same maybe as I was saying. Is the monitoring interconnecting with an alarm system? Is there a risk that it will happen so quickly that it creates a hazard on the roads? And is there a reason to have a blocking post? So a few questions in one.
Okay. Excellent, very, very good. So we are in the progress of implementing this with the road administration. So they are in charge of dealing with emergency services. So we are more in the research part of this at the university, and that connects to their internal alarm system at the road administration, and exactly how that works, I'm not entirely sure. There is a risk that the landslide motion will happen quickly, and because the road has been there from 1968, we know there are some examples where there has been quite rapid motion, which has created offsets or displacements easily of about half a meter or something like that on the road. So if that happens during the middle of the night and someone is driving there, that's a real major hazard. And it doesn't take necessarily a big part of the landslide to move. It can be some of these small segments that are in the northern part of the landslide where the slope is steep and the road is standing quite high. It could deformation there can happen quite rapidly and of course lead to accidents. If you have, let's say, 20 centimeter offset in a road and you're driving there at 90 kilometers an hour, that will make your car jump quite a bit.
Okay. Yeah, there's another question is here, medium budget. What technology would you choose with high budget and what would be the benefits?
Yeah, it's a good question. So if we would choose high budget, then we are basically choosing the same kind of instruments that we are using when measuring plate motion continuously and some of the volcanic deformation. So they are just more expensive instruments, and the benefits from we didn't really know what were the benefits. We had been running these kind of instruments for about a year before we went and bought them for this project. So we had seen that the results were quite comparable, and I think the result of this work is that it's actually maybe a less difference than we would expect. So this medium budget instruments, they give us very comparable to results that we would get with sort of higher level instruments, but we have yet to test how that is for the real-time processing. It's a possibility that the better antennas behave a little bit better when we're doing the real-time processing.
Okay, and one last question. You talked about this happening all around the world. Is there some network? Are you talking to people around the world about this, or are you each working in your corner trying to solve the issue?
There's a very active research and monitoring community in landslides all around the world. So there is communication through that, and it's great to have people here from the Nordic countries. So we and especially my colleague Thorsteinn works a lot with Norwegians, and so there's we can learn a lot from them. So I think there's good synergy between different landslide groups around the world. It's a hazard that is just everywhere.
Yeah, that's great to hear. Thank you, Walter. We will move on now to the third presenter, which is Víðir. We usually call him our one and only Víðir Reynisson here in Iceland because he is the one in charge of telling us everything about what's happening with our volcanoes and other things. So Víðir is the Chief Superintendent at the Department of Civil Protection and Emergency Management in Iceland, and he will talk about the mobilization of emergency fleets during volcanic eruptions and more, I guess. Over to you, Víðir.
Thank you, and it's very nice to have the opportunity to meet all of you today. I'm fixing my technology here, so I hope that this is working now. You see my slides. So yes. I will start to talk a little bit about volcanic hazard and risk and how to prepare and the cooperation that needs to be done to get that working. First, I would like to thank a couple of co-workers that's been working on this with me. I'll start with the people from the Road Administration of Iceland and the University of Iceland Institute of Earth Science, colleagues of Halldór and himself. of course, from the Met Office, who is kind of responsible for monitoring, and then 2 engineering offices, Verkis and Epla, who's done a lot of work for us in this. And then photos I'm using in the presentation is from COC, who is a photographer who is specialized in taking pictures in disasters. So let me see. So this is kind of our hazard map for Iceland. You can see that we're dealing with everything almost. We thought for a while we were not dealing with forest fires, but now that's one of the things that we are working on a regular basis. But when we are talking about preparing for disasters, we have this triangle or pyramid of which should lead us to a safe and secure society, which means that you have to start by analyzing risk and vulnerability. You have to work on risk reduction, contingency planning, preparedness, everything that most of you probably know, and the 2 presenters before me touch upon this also, because that's what they are doing in their work. So what we also do is that we like to take scenarios and work with them and see how things, what can happen. So we start with thinking about what we know about the scenario that we are looking at, and then we probably find something that we know that we don't know, and then again what you know that you didn't know, and then the most difficult part is what you do not know that you do not know, and that's what we call the black swan, or usually ends up in the major disaster that we are surprised by. So, and when looking at preparedness in Iceland, and I think in all countries, key factor of success is to develop a couple of things. First, everybody who is working on it, on the scientific part, and all the way to the operational part, and the inhabitants and everyone, tourists and everyone who is around the area that we are looking at, must kind of trust each other and trust the information that they have. And when we come to roles and responsibility, it must be quite clear who has the different roles and the responsibility with it. And I think what, like Halldór mentioned here earlier about the monitoring and then giving the information to the road administration, who is responsible for closing the roads, and then also for the responders to know what to do. So that's quite clear and very important. And then the last thing I would like to mention is open information sharing. It's quite it's really valid for us all to be able to share information and to be open with it and don't have any secrets. And even though I'm not quite sure about what kind of scenario we are dealing with, it's important to be open with it and share the information as soon as we know it, and with the limits of the unknown in that. And also you have to look at it when you're dealing with disasters or prone disasters. You have to find out who are the stakeholders and who are going to be your partners when you look at it. And both can be nationally, it can be both from the public sector or private sector. And also you have to look at the international partnership. And this is for Iceland, especially when we look at volcano crisis, it's quite important because we have seen in some of our volcanic crises the international effect that has. And then I'm of course referring to Eyjafjallajökull in 2010, when with all the destruction of airstrike that had. So again, this I can't talk enough about it, that all partners must think of their role in this as important, and they need to be acknowledged in this. And when you're preparing for things, you must involve them in the whole process, from the risk analysis to the operation plan and to the information sharing. So I'm going to give you 2 examples today. The first one is about the risk assessment that we did in close cooperation with the partners I mentioned earlier. for Eyjafjallajökull and especially from Katla, which is one of our most dangerous volcanoes, who lies underneath 250 meters of ice. And during this hazard assessment, we looked at different eruption types, the frequency, and the most danger that we looked into was the flooding coming from it, because when you have a volcanic eruption underneath a glacier, you will have a lot of meltwater who needs to go somewhere. And we looked at it that, and when we were calculating and simulating this, we were looking at the infrastructure that could be in harm's way of the flooding. So we have three main flood routes coming from Katla or Mýrdalsjökull, and all of them will end up in at least some populated area, but all of them will go through our main road number 1, and having floods like this glacier outburst flooding will damage the roads and damage all the infrastructure in its way. And fixing the roads is one, but when you come to fixing bridges and other things, that is quite a challenge. So I'm going to show you a short simulation of one of the types of flooding that we are preparing for. This is going through a quite populated area. It's one of the it's a country area with a lot of farms, a lot of tourist attractions, and a lot of infrastructure in the area. And in the simulation that you're going to see, the colors in the simulation show you the depth of the flood water, and the timing from the start until it hit the main roads is about 4 hours. So let's see if this works. And you can see the flood starting from the glacier coming, and the most depth close to the start is about 50 meters, then it goes to 10 meters, 8 meters, and then it started in this area to be in a populated area. And you see some roads there, country roads closed, and the red line that's approaching now is the main road. And it's in about 4 hours, goes over the road. More country roads and a lot of farm area that would be flooded in this kind of a flooding. And where the flood is hitting the sea now, there's a harbor, which is a ferry harbor to the Westman Islands, south of Iceland, which will also be hit. So you can see this is one of the scenarios that we've made. It is based on the science, based on former floodings. We had floodings there some thousands years ago, but it's a huge thing, and the damage would be really much. And if you only look at the road that in that area that would be flooded, I think it's about 10 or 12 bridges that would be damaged, which takes lots longer time to fix than roads. So this is a scenario that we've been preparing for, and like I said earlier, we have 3 other flooded areas that we're looking at. So the main thing I'm going to talk about today is the Reykjanes Peninsula, and in 2020, in December 2019, we started to monitor changes in the earthquakes. We saw changes in the GPS. We saw changes that could be predicting that we were looking into some kind of erupting periods. As our long-time risk assessment for Reykjanes says that when it starts to come up volcanic eruption in the area, that would be something that could take decades, from 40 to 400 years, a period of time that we would be dealing with this kind of situation. Totally different situation than we've seen in the volcanic eruption underneath the glaciers, where we would have ash clouds and explosive periods. This is more lava, and almost the only lava almost, and the risk and the hazard will be quite different. So we started to monitor this very closely in January 2020. And in March 21, we had the first eruption. And up to now, we have 7 different eruptions in the area. One still ongoing. And it's almost stopped. It's very small at the moment. But at the same time, we are waiting for a new period, a new scene to start. And if I show you a short picture of a very simple picture how this can now Halldór, who is here, this is in his expertise of monitoring. But what we have seen is that of 25th of October 2023, something happened near Svartsengi, near the mountain of Þorbjörn, and we saw magma started to accumulate in the magma sill. And 10th of November, we had an episode that was ended not in an eruption, but we had this magma on the move, and they had a huge damage in the town of Grindavik. Then we had on 18th of December, 14th of January, and 8th of February, we had eruptions. Then we again had magma on the move on 2nd of March without an eruption. And from 16th of March, we have had an eruption ongoing. So at the time that we have seen these different episodes on the surface, there has not been a major change in the flow of the magma from the deep down, maybe from the crust and in this magma sill. So we say that the valve opened of 25th of October, and it is still open. And that's the thing we're looking at, and the information from in the media and from some scientists, they're always looking at what is happening today or tomorrow. But we at the Civil Protection, we are looking months, years, and maybe decades ahead to see what's going on, and especially looking at the effect that this can be have to the infrastructure. And I'm going to show you some pictures of that later on. But a little bit more of graphs from Halldór and his colleagues, both from the Met Office and the university, where they are trying to model, based on the GPS, based on the infrared radars pictures, the volume of the magma that is under this, or in this magma chamber or magma sill underneath Svartsengi. And we can see that from the last eruption, we have had inflow around maybe 10 or 11 million cubic meters, but these modules are looking at what is the total volume of the magma that could be in this sill, showing us that it could be almost 24 million cubic meters. And when we have those episodes that we see then on the surface, some changes in an eruption or not an eruption, is what we are always looking at. So at the same time, now that we're looking at an ongoing, a really small eruption, we are waiting for another episode of maybe a big or similar eruption that we have had, which have up to now had a quite effect on our infrastructure. And that's what I'm going to talk about for the last part of this presentation, is the episode that opened up and had real effect on the surface. So this is a picture where many of you have seen, I believe, is on the way on the road to Grindavik, which was flooded by lava. This is from January this year. And it's almost like it's photoshopped. The lava is photoshopped on the road, but it is not. It is an actual picture of what was going on. And this is from another view. And the lava reached the road, I think it was 4 hours or something from it started until it went over the road. This has happened twice now. So this is one of the challenges that we have, that if we look at of the infrastructure that we are dealing with, the roads is one of the things, the power lines, the heating pipes, and the power plant, which is very close to this this area, and the communication systems are all of this is at risk when we are looking at this. But what is so I've been admiring people that's been working on this on the scene, because in this episode we have seen men and people fighting nature with the technology and the knowledge that we have, and trying to change the way the nature wants to go. And in some way it has been a success, in other it has not been. So these are pictures taken from at the same day. You can see the front of the lava, and you can see the road. One of the roads in the area lies under the lava already. And if you show where my pointer is, these are barriers that we've been building to protect the power plant, which lies in the picture on the top left corner. And these are roads and infrastructure in the area. You can see all the equipment there that has been mobilized to protect the power plant, to protect the roads, but sometimes nature just goes their way. Another picture from a different angle, taking a similar time, then you can see the vehicles and the equipment in the front of the picture. They are working to protect the heat with one of the pipeline that carry hot water from the power plant to a populated area, about 30,000 people. Now this is in January. This is the weather is not that day was quite bright, as you can see on the picture, but it's -12, and we knew that if the lava would reach the pipeline, about 30,000 people would lose the hot water. In this picture, you can also see power lines. If you can see my pointer, this is power lines coming from the power plant. We have already built barriers around that, and you can see the barriers on this area what we have built to protect the power plant, to divert the lava. At this time that this happened, we were in the middle of renewing the pipeline to make it more safe for, and could be able to deal with the lava. But the problem was that we haven't buried it in the ground as we are going to. So we were in the middle of this protective work when this happened. And as you can see, the lava is quite close. It was coming about 700 to 800 meters per hour. And you can see in the background, this is where the eruption is. So it's not quite long, not quite far away. So here is another picture. You can see that we have not been able to bury the pipeline, but we're almost there. 6 to 8 hours more than we probably could have saved the pipeline. But you can see the power lines, see all the equipment that's been using to try to protect this area. But at the same time, we were able to protect the power plant itself and the roads in the area of the power plant, but we could not save the pipeline. So we lost the pipeline around midday of that day, and for a couple of days, 30,000 people were out of hot water. But by a really impressive work of so many people, we were able to build a new one around the lava and get the hot water flowing again within a week. You can see this from another angle, and you can see in the distance is the power plant, and you see the lava. You can see the barriers, and see all the equipment that is there. You can see the road that is the construction is ongoing. Is one of the road that we needed to have to be able to work in this area. So what happened just a couple of days after the lava had run over this area, we had fixed the road. I always say we, because it's a cooperation of so many people. Of course, the heroes of this stories are the guys and the girls on the trucks and the bulldozers that made a new road over the lava within a couple of days that the lava ran over there. You can see the steam coming from the road. So this is just one example of what we need to deal with when we have volcanic eruptions in Iceland. And the good part is that in our risk assessment, in our plannings, we had seen that this could be one of the things that could happen. So we had the equipment, we had the knowledge, and we had the people with the skills to work on this and to solve the problems that came up. A couple of more pictures. You can see that already on day 2 we had already traffic on the road, even though it's almost not a road, but still it is. We could start to deliver goods and keep the traffic flowing for the companies and other in the area that needed this line of transport. At the end, I'm just going to show you 2 pictures of what is, in my point at least, a quite interesting job that we're doing in cooperation with the road administration and the ESOR and the university and a couple of the engineer offices that I mentioned earlier. Is that when we on 10th of November, when we had the first episode in this period of eruption, we had a major change in the land in the town of Grindavík. We had fissures open. We had I don't know, 200 houses damaged, and then we had this uncertainty of what really happened under the ground. So even though at some time we could see it on the surface, we found out in the upcoming weeks after this that under the ground, even though the surface could be quite smooth, there was a huge hollows, huge cracks just a couple of feet, a couple of meters under the ground. And we're using a real advanced technology, both like these pictures are showing from drones, but also in other equipment that has been used in different tasks. But combined now, we are scanning the whole town of Grindavík and the whole area around it, every square meter, and seeing 25 meters down into the earth to see what lies underneath. Because on the surface we see this, and this is quite obvious, a danger that is a huge task to fix and to make the road safe again. But in many places that we have seen in this area, have we seen that even though we don't see it on the surface, this equipment has shown that there is hollows, there is cracks under the surface, which then might open a little bit later. But as we have seen now, we have seen vehicles being trapped in them when the asphalt break or something like that. So there is a lot of risk there that we need to identify with this equipment. We have finished scanning all the roads, and now we're scanning, the area close to it, and the third and fourth part of the scanning, which will last all the summer, is open area, playgrounds, sports area, and all this in the area that needs to be scanned to see if it's safe to be there. So, for example, what you see on this pictures is taking early this winter, but this crack that you see there is when we have digged it a little bit up, opened it a little bit up, it lies about 25 to 45 meters deep, and it is 6 to 8 meters wide, where it is the widest part of it. So this concludes what I'm telling you. I really like this picture. It's from what we call the lava road. It's one of we have 2 roads now lying over the lava, which is open for general traffic. And this shows the situation. It happened just a couple of minutes after we had a rain shower. You can see the steam coming from the lava, and just one of the inhabitants of Grindavík going back home through a road that's already been made on lava, and I think about 25 centimeters depth there is about 800 degrees warm lava. So thank you.
Thank you very much, Vidar, for this presentation. It's almost like a futuristic movie pictures you have here. Questions to Vidar? I will start with one. I'm just wondering, with all these natural hazards that we have in Iceland, do we have enough people to deal with this?
Well, the short answer is no. You probably never have enough people. But I remind you on the numbers that we saw on the first presentation from Norway about every 1 Nordic krona that you put in preventions is saving 7 to 14 in the cost. We have seen similar things. We have, for example, the barriers that we have built. They have already saved at least 1 to 14, as Norwegian number is showing. So that's a really important thing. That's something that we are lobbying with politicians, and our Minister of Justice, which is responsible for our part, is been quite positive and already almost doubled the staff that we have. So that's a good thing. But I would like to have more, but this is the first step, at least. We are quite few at the office at the moment. It's a really small office with 10 people, but we are now getting closer to 20.
Okay, that's good to hear. There's one question in the chat as well regarding the Katla example. Can the flood from the eruption under glacier cause such a big tsunami when it hits the sea that it causes damage to Vestmannaeyjar? If so, are there any plans for warning systems in place?
Excellent. It's an excellent question. We've simulated it if the water itself, the flood water itself, if that could cause a tsunami. And we have an example when I think it was in '96, Halldór might remember this better than me, then we have the Gjálp eruption and the flooding in Skeiðarársands. We took away the bridges in Skeiðarársands, a volume of 1/3 of that we could see in Katla, but there was no signs of any tsunami or waves after that. And we have had some calculation, but this could not happen. But what can happen is that the mud that comes with the flood water, it builds up a new land. And for example, in the Katla eruption in 1918, we had 3 kilometers of new land from the coast. And this is a very unstable part. And if it collapses into the water, that would cause a tsunami. And we have examples from 1755, if I'm remembering my history right. We had floodings in Vestmannaeyjar, we had floodings in Grindavík and other parts with the south coast. Couple of days after an eruption in Katla, and the scientists say that is probably caused because of this new land is so unstable that it falls down. And somebody explained it to me that if you fill your bathtub with water, put your hand just under the surface and then push it down, you'll see the wave coming. And that's kind of a tsunami that could be caused by this. And yes, we have plans for this and warning systems in Vestmannaeyjar and in Grindavík.
Okay, just a side question to this. How about the general public that's underneath, living in the flood area from Katla? Are they informed as well?
Yes, we have quite frequently, we have what we call people meetings in the area where we go through the evacuation plans to make sure that they are up to date. And because the timing is so short in this that that all the inhabitants play a role of first responders also. So they are, if you're a farmer who lives closer to the mountain and you have to drive past a lot of other farms when you're going out, your responsibility is to make sure that everyone in the way knows that this is happening and they start the evacuation process. So everybody's involved, and every 3 or 4 years there is people meeting in the area where we go through all these plans.
Okay. We have one more in the chat. How do you coordinate and prioritize construction work in the middle of an eruption? There must be multiple contractors.
Yes, we have. in the Grindavik scenario, we have, I think, at some time we have the 8 biggest constructors in Iceland working on it. At the moment, I think there is six different companies, and at one time we had all the biggest bulldozer in Iceland working there. Oh, I think they're 120 tons. I think the biggest one that we have, and I think we have 4 of them or something like that, and all of them are working in this area. So that's the only way to make this possible, is to have everyone involved with every special equipment that is possible.
Okay. One more here. A very impressive presentation. Question: how does the risk of natural catastrophe influence the important travel industry in Iceland, or is it maybe just increasing the interest to travel to Iceland?
It's an excellent question, because it's always to find the balance between informing people and scaring people. So you want, at least what we do, and that's what we're working with the tourist industry a lot, is to make everybody know what's going on at each time in Iceland, to make sure that they get the source of the correct information. And I think it's almost all tourists that comes to Iceland come to Iceland to see the nature and to live the nature. So when we have something like this, the interest increases, but at the same time we need to make sure that people who's coming here is safe. And we have a really good cooperation with the tourist industry in that. And both to like I said, share the correct information that Iceland is not burning down, as we have seen in some news that we have all been evacuated, which is not quite true. But at the same time, to make sure that the tourists know what to do, know how to behave, where can they go, what can they see, and where can they be safe.
Okay. Yeah, time is flying. Thank you a lot, Vidar, for this interesting presentation. We will move over to Finland now to talk about extreme weather. Over to you, Jani Putainen, trying to pronounce this, Head of Group Traffic and Media at the Finnish Meteorological Institute. You're muted.
Yeah, now should be okay.
Yes.
Just a second still. I will shoot this presentation. It's full screen, right? So, good afternoon. Well, my name is Jani Poutiainen from the Finnish Meteorological Institute, and today I'm going to be talking about the extreme conditions, a little bit different angle than the previous presentations we've seen. I'm working as a group leader in our institute, and our aim is to say, well, we serve the whole public of Finland, but also we have the capabilities of adjusting our services in a way that they can be further tailored in various ways. And I will try to describe maybe the both angles in these presentations, and what we do in our activities. And I'm really sorry to interrupt my presentation, but my doorbell is ringing really heavily. I will just have to take a 7-second break. Please forgive me.
Okay, no problem. We'll just keep on talking here. Jenny, do you have something you want to say?
I think this is so interesting that we need to continue the kind of a thematic approach in the autumn as well. So we look very much forward to what Jani has to say as well, because we can make a short summary after his presentation. Thank you. Okay. Now he's back.
I'm so relieved I could make it. Well, things just happen sometimes, right? Anyhow, yes. Let's go on with this talk. And now, to give you a brief overview of the Finnish Meteorological Institute's activities across the whole of the Finland. So Here's an illustration for that, and I may point out that various transport modes are in the center of it, how we see it. And also thinking about the extreme conditions anyhow, you could locate some icons for rescue authorities and similar activities related in our view, what all kinds of actors are involved whenever something really drastic is happening, whether it comes due to atmospheric phenomena or sea or even space in our cases. A few more words about that a little bit later on. Aviation, marine vessels, rail traffic, land traffic, cars, and all of that. And the ITS community would be really, I think, something that I think can be even more utilized in our society and all of the businesses and industries to make best out of the information that's available and is accessible and can be used to enhance the safety especially. And what we present ourselves oftentimes is that we make a note that our institute both is a research institute, but also runs operational services. And I'm from the operational services side myself. Thinking about the ITS and traffic overall, we have several research groups specializing in developing the methods and specifically observation and forecasting methods of various atmospheric and sea phenomena. And that is something that we want to utilize and make and elaborate so that it could be readily available for alerting companies, people, and all. But what's coming up next is something that we deliver through this Weather, Sea, and Climate Service Center. And in that respect, we have this public view with standardized methods, I would say, and standardized services and products. But then there's also the capability of making this machine readable opportunities for other operators and making the longer information chains in various devices across the various transport modes. Still illustrating a little bit about this view, we have the general views, thinking about the public web pages, for instance, or certain applications, TV, radio, and other electronic media. That's the other end. And on the other end, we made accessible tailored ways of utilizing the same information. Maybe a notable detail in this figure is that there's even a so-called road weather center we are together operating and assisting with the Finnish road company that's utilizing the weather-related information in the maintenance actions of the road network. And also a notable detail in this figure is that there's also a lot of so-called open data sources that it's accessible to anybody for any purpose, whoever wishes to utilize the same in any of their information type of services, or then in any decision making or integrated systems. The heart of the actions, I would say, especially when it comes to the extreme conditions, is FMI's Safety Weather Center operating continuously. And here is concentrated knowledge and expertise, how we can be alerted and alert others when it comes in any of the hazardous weather, let's say. But in particular, they also operate a flood center in the same premises. There's a global monitoring center for natural disasters covering following up of various global hazards like the ones that were described earlier in earlier talks, which may not be as profound in Finnish environment. We don't have volcanoes locally and so on, and we don't have high mountains, so that affects on the phenomena that most worries us. Although, of course, many of the phenomena, on the other hand, are crossing the national border, so we want to be alerted on broader sense as well. We have Climate Center and then Global Space Weather Service for Civil Aviation, and this is this space weather. Also, another view for what's can be considered extreme if we have such, for instance, solar events that disturb GPS location on a radio transmitted any information that could be extreme and cause multiple effects in later on in various information chains. Well, then one might ask that is there severe weather in Finland or extreme weather? And one way to approach this is that have a look at the number of the emergency calls, and I have here some statistics from the past years, and note that on the average, I'd say at least 5,000 calls per year, and they are topping like more than 10,000 emergency calls per year, and these are somehow caused by a weather event. So there's a lot of happening oftentimes in Finnish society and Finnish rescue authorities and many other, well, all of the people more or less who are moving, whether it's road traffic or any other traffic. From this slide, another view or another point and I wish to make is that one could see there's a cyclic patterns or some peaks along the year cycle. In summertime, say June to August, there's one peak that's resulting from summertime phenomena, especially the lightning and thunder, heavy rain and similar things that make the disruptions bigger, and this certainly has a really big effect, for instance, in rail traffic and many other modes of traffic as well. And the other peak would be in late of the year, in November, December, even higher numbers for disturbances caused by weather for the say early winter storms, the deep low pressure areas that develop and approach from the west, typically to Finland, and so we also have to really pay attention and be alerted on these matters. And what happens there in our safety center, I've circulated in this slide those phenomena that have a direct effect on various modes of transportation: the high winds, thunderstorms, heavy rains, weather warnings for pedestrians. Well, that refers to slipperiness, actually, also related to road safety and traffic weather warnings, as also specifically stated in the slide. On the seaside, marine traffic, we have a sea level water disruptions and rough waves and ice accretion. Also, ice is typical to Finland. As an Arctic Sea, we have along our coast, and that I would say also can be extreme, even though not say life-threatening as such, but it can have drastic impacts in other ways, and that has to be handled for the traffic to be able to go smoothly. And all of this, something that's initiating from the safety center, we can distribute through various web portals and machine readable interfaces. And this is something I feel like could be a matter of discussion within the ITS sector, that what's this best utilized. And I've listed some of the places that you could find of this data already. This whole process or the on-duty forecaster's view is such that one is all of the time being prepared and having an outlook from present state up to 10 days or so, and we are having separate outlook products that can be arranged for the interested users to be to internalize what's may be coming, what dangerous may be coming. Then when the actual things start to happen, we talk more about the warnings and actual notifications that are being sent out to all of the subscribed users. And once again, this involves all of the transport modes. And after the events have happened, we typically make some analysis what's been going on and maybe add an additional press releases of these events. This one is something that would be the one in the previous slide. It's something that we send out when the case is on. And in this case, this is from April someday this year, an event when we have the heavy rain, snowing happening, and it resulted a lot of traffic accidents and very bad driving conditions in certain parts of the country, south and eastern parts. And this is something that our meteorologists produce all the time. They follow up how the event is developing, and they describe quite in detail what's going on and update as new information comes along, and also estimate of the impacts for traffic modes, in this case especially for the road traffic. And this information we distribute out through the emails as notifications and the customer portals, and can be accessed on machine readable, well, similar types of information through the automatic channels as well. We oftentimes refer to the term luova, which actually means the national hazards caused by weather, or national hazards overall. And in addition, what I've described there, we have this broader monitoring across the globe, and this is produced together with Finnish Environmental Agency, which are more looking at the floods, and then the University of Helsinki, which is more looking how the earthquakes will develop. And then for these three organizations, we put together a so-called luova system that this information is aimed at other authorities and ministries. So this is not part of the big public distribution, but forms an important extension spatially. I have a few points from different transport modes there. First, having a bit of a look on road traffic, and this relates to the organizations in such a way that we also develop these methods and services and forecasting models in-house. And for instance, for the road traffic, the really central source of information is so-called road condition forecasting model. That is a special type of model which is being run on top of the other atmospheric models, and producing such a detail that is really of a special interest of the road users, whether they're cars or pedestrians. Of the extreme side, we see that the freezing rain events, freezing drizzle, for instance, and of course the slipperiness, icy roads, and those ones are the ones that really oftentimes make the most dangerous events actually in the traffic, and we could see tens and tens of cars colliding sometimes together. Not every day, of course. For the marine side, we on the same premises and our safety center, we have maritime specialists who have expertise in this. And in Finnish environment, the icebreaker assistance and anything related to that, even though not as life-threatening, but still really extreme for us and necessary to take good care. This is something that we provide also through the warning systems, open water, or whether it's a winter time, whether it's a summertime. Wind and waves, of course, is something that caught really the bad situation out in the sea, also or near the coastlines of Finland. And thirdly, the aviation, which is probably the most sensitive of them all. So there are lots and lots of various events that disrupt the weather. And just a few weeks back, I was flying from Europe to Helsinki, and then we also had already spring happening, and all of a sudden really heavy snowing happened, and all of the flights were cancelled or delayed and a lot of times. So this is also something that the FMI is doing to ensure the safe traffic, air traffic. But it's not all, because we in this figure we can consider ourselves as being a weather service provider, but we need to have the other parties involved tied in this whole setup, because in order to get the overall benefits out of the forecasting or warning or alerting, there needs to be capabilities on both sides, both the producer and both the producer and the user. So we need to be making cooperation in there, and otherwise the useful information, how useful it can be, it cannot be benefited in the end unless all of the steps, both say the attitude and the technical means are in place. And nowadays we really much focus on the modeling of the impact, which is in this figure in one of the middle steps that needs to be fulfilled to get the whole potential out of this production of any such information related to weather. But the modeling of impact means that we aim not only to forecast the weather events like wind, heavy wind alone, but we try to gather the relevant traffic system information together with weather forecasting, weather information, and use the machine learning models and artificial intelligence methods in order to renew the end productization such a way that we can even, in particular, forecast few days in advance. For instance, any decision-making situation the traffic user may have, and a practical example would be whether or not start snow plowing activities, or whether or not in maritime environment, for instance, whether or not case is such that the marine pilots can be operating or not, and not really the waves, but the decision whether or not can be piloted or not. So this is something currently happening a lot, and I will finish my talk in this impact forecasting topic, in which we see that we could be maximizing the weather-related information and making it even more easier to use. Anyone who is in the position that needs to make any choices or select any choices, could be professional user or could be a common citizen. But for this we need both the weather information and the traffic information. And we have made several of these, and we have up and running some. And one of the examples is shown in this figure, and it's quite late spring from the start of April now, but this one is the picture he is showing 6-hour aggregated number of forecasted road traffic accidents. So not slipperiness, not heavy snowing, but accidents. And one can see that there's even if this late of spring we have been having a coming dangerous event in Lapland, showed by color coding, and the numbers you see there, the forecasted traffic accidents in those regional areas. And this is something that the model that we teach with the traffic accident statistics, and this is running. So we have similar ones, and the similar ones can be also further developed. Of those that we have, the pedestrian slipperiness is something that is running as well. But now we are looking more of the summertime events, I would say, and then in there could point at the damage prevention task for the rescue authorities, something that can be forecasted this way. And I think that was the last one. Thank you.
Thank you, Janni, for this interesting use of data and forecasting. Any questions out there? Opening the chat. We have a hand raised. Bergþóra Kristins.
Yeah, sorry. Thank you, Janni, for a very interesting presentation. Some of the things that you are doing is something that we are considering here at the Road Administration in Iceland. So we are very interested to hear and learn a little bit more about how far or how long has this process been to get you to this place now?
Yeah, this is of course an interesting question in a sense that this is a fairly new thing. I would say that we've had certain development projects piloting the thing for say maybe 2 years ago we started or so, and the original development projects have been finished, and as a result of that we've obtained those results that I showed. But now I feel that we have the knowledge and capabilities to extend and further if we find a new use cases and where the data is available. And that's one of the key points. I'd say that in order to go on this route, one needs to get enough of the volumetric data for long enough of time in history, and that seems to be a little bit of a challenge sometime. And once that is gathered, then the rest is easier once the method is defined. But it's I guess the whole area is developing really fast nowadays.
Thank you. We are just started. We have only been looking into one section or one valley, should we say, collecting data for 2 years now, and we are very interested. But at least I haven't thought of connecting it straight to accidents, just on a road condition forecast. So this is a new way of thinking. So very interesting to hear.
I think one of the notions I've made myself at some point is that we talk in many arenas a lot about AI and machine learning, but in very many times they are related more of the data as such, or sort of analysis of the data or picture image type of data. But what's the difference in there to that? What we've been doing is that we have coupled the learning to actual forecasting model. So that brings a dimension of the forecasting there, and we've heard really good feedback from the users and the potential users. But this is the area where I feel like that it's ITS community, but many other communities as well that could be benefiting of these methodologies once they just can define their problem and find the learning data.
Thank you. We have one question here in the chat. There were a lot of calls and people having problems. Where do you think the main possibilities to improve this lie? I'm not sure if... Yeah, it says in Iceland, roads are often closed too late as there's difficult line between blocking people's journeys and protecting them. What policy do you have on this? Do you close like sooner or later?
Well, I would have to say that we work together in these matters, well, not alone for sure. And in particular, we deal with traffic management operators of Finland, which is another entity. But together, we send out the announcements for the traffic, and we specialize more of the weather side, and then for the traffic announcements come from the traffic management centers oftentimes. So this is the way, and we send out from the FMI side, we send out the warnings as soon as we realize that something will be happening. And I will refer back to the slide where I had this outlook, and then when it's actually happening, and then the aftermath. So we are alerted ourselves all the time, but maybe let's say, we try to be warning earlier on and give out the early signs rather than late signs. And prepared in advance, I would say, if I need to make a selection.
Thank you. I think we have to have this as the last question today since our time is running up. There's a question if the slides will be available. Well, the recording will be available. Jenny, how are we dealing with the slides?
The PDFs of each presenter will also be available. So, Jani, I know you shared yours, but I need them as a PDF as I couldn't open them. So please resend them to me.
Okay.
We will upload the recording and the presentations. Thank you all.
Yeah, and just maybe a quick summary of what we've listened to here today. I think my main take from this is that this is a long-term process to gather data, to be able to analyze and then utilize it in utilize the technology to help us and rescue us, but also to save money, because we've heard that every krona put into the prevention and the research returns, was it 7 to 14 Norwegian kroners? So yeah, just that. I think that's the main take, and I think ITS is plays a key role in all this.
Definitely,
combining this, and also the networking that we're seeing taking place here. Jenny, do you want to add something to this?
No, I think that was a very good summary, Lilia, and I thank you for a very good moderator, and I thank everyone attending, and thank you for all the good presentations, and I hope we can share your contact details if someone asks, and be in contact, because I think knowledge, we need to share that in order to move ahead. Thank you so much to all of you joining today.
Yes, thank you for your time, and have a nice afternoon.
Thank you.
Bye-bye.
Bye-bye.